the subject is the end of theory. It sounds rather emphatically, and the subtitle is Will Data Deluge make and machine learning make the scientific method obsolete? All right. My main points. The aim is to explore the influence of recent developments in data science and machine learning. Sorry, I have to minimize this window because I do not see anything from my presentation. Okay, now it should be fine. More specifically, I'd like to discuss this possibility that due to large amounts of data and the use of machine learning techniques, it's possible to build successful models in scientific research capable of predicting phenomena without using scientific theories. In other words, do we already witness revolutionary change in the way science is done? That is, are scientific theories becoming obsolete at all? Now, my main points. Last decades witnessed a process called data deluge, deluge. I don't know, it comes from bloody French, from French. It's also called data revolution, and some describe it as a new fourth paradigm in doing contemporary science. Anyway, stress moved from theories to data, and this is, of course, a new severe challenge to data science and machine learning. Apparently, sorry, next slide. But some, like Christian Anderson, mentioned in the reference list on the last slide, go even much further in their optimism about successes of data science in scientific disciplines and announce the end of theory, believing that large amounts of data and good machine learning algorithms are already making scientific theories obsolete. But not so fast, I say. In the paper, I'd like to show that this optimism is, to put it in a delicate way, premature, because this stance can be severely criticized from both philosophical and technical or technological point of view. Now, a few words about the data deluge. The British Royal Society and the Alan Turing Institute published a big report about entitled The AI Revolution in Scientific Research. It summarized it summarized the workshop held a few months earlier, a few months before, summarizing 5 or 10 years of AI research in science. It starts by admitting that by processing large amounts of data in fields such as life sciences, particle physics, astronomy, and so on, machine learning is starting to play the key role in many fields, pushing forward the boundaries of science. Paradoxically, as it's well known, new machine learning techniques, especially deep neural networks, work best on large amounts of data that contemporary experimental science abound in. But the phenomenon of data deluge was noticed much earlier, already at least in the 1999, at the time of publication of a collected book under a very emphatic title, The Fourth Paradigm, in which, in a large introduction, Jim Gray, a world-famous legend of data science, missing at sea, by the way, around the turn of the century, distinguishes 4 paradigms prevailing in various periods of the development of science. Jim himself always keeps saying, I'm showing this picture every time when I talk. Okay, I stole his picture from the book. My apologies, because it's really convincing. The four periods are some thousand years ago. We had paradigm one. Science was mostly empirical and mostly consisted in describing natural phenomena, putting down position of stars and planets, for example, in astronomy. Last few hundred years, this is a favorite theme for philosophers of science. Yes, science was dealing with constructing high-level theories, mathematical models, generalizations, then trying to draw some empirical consequences to test theories or refute them. Yeah, Popper would be pleased. Newton, Einstein, many others. So we have high-level mathematical theories with high mathematical models, and then generalizations, and then some consequences. But in contemporary science, since a few decades at least, we have computational branches of science, simulating phenomena, modeling phenomena. This is called the third paradigm by Jim Gray. And in many disciplines, it's the only thing we can do, because actually theory is missing, or if not, it's very difficult to draw direct consequences from theories because of mathematical complexity. But since a few years at the time of writing the book, Jim Gray distinguished the fourth paradigm, rapid development of data exploration, called e-science, which unifies theory, experiment, and simulation. Data is captured by instruments, for example, Hadron Large Collider, or complicated telescopes, if I can call them telescopes at all. Generally, it's captured by instruments or generated by a simulator. Then it's processed by software, then stored in a computer, and finally analyzed by specialized programs. And then scientists only get to look at their data very late. Okay, this is the fourth paradigm by Jim Gray. But anyway, it indicates that in contemporary science, stress moved from theory to data, more specifically big data analysis with machine learning techniques. Okay, but how about theory? We have data, we have ready-made solutions for data processing, for detecting irregularities, for detecting important things, and so on. Historically, science has progressed by first generating hypotheses or theories and then collecting data to confirm, sometimes vice versa. But anyway, theories had a very important role in it. However, in the big data area, ample data which is being continuously collected without a specific theory or hypothesis in mind, for example, because there is no hypothesis at all, offer further opportunity for discovering new knowledge and predicting new phenomena. The role of data science in scientific disciplines is beginning to shift from providing just simple data analysis, for example, detecting particles in Large Hadron Collider, to providing ready-made, out-of-the-shelf, full-fledged knowledge discovery frameworks, for example, in bioinformatics, climate science, earth sciences. Now, based on successes of data science in mostly commercial applications, and predicting trends in commercial industries, such as retail, advertising, for example, there is a growing anticipation of similar accomplishments in scientific disciplines. Now, still the fourth paradigm, the end of theory. Okay, some, like already mentioned Christian Andersen, go even further in their optimism and say that and announce the end of theory. They believe that large amounts of data make it possible to build successful models capable of predicting phenomena without using scientific theories at all. Now, what can we say about it? I will say not so fast. This view can be criticized both on philosophical or methodological grounds and technical grounds. I don't know which grounds are more important, but both are. For example, Deluge criticizes this view and rightly points out that this position results from misunderstanding of the objectives of science and the goals scientists want to achieve. Science, he says, unlike advertising, is not about finding patterns. Although this is certainly part of the process, it's mostly about finding some explanation for those patterns. If we stop looking for models and hypotheses, are we still doing science? In fact, it's easy to understand that Andersen is wrong even about advertising. I mean, without models, mathematical, conceptual, data are just noise. So far, Deluge. Well, I agree, absolutely. Science differs from advertising. We do not only want to predict new phenomena, we want to understand somehow why they happen, why they behave that way and not this way. Now there are much more serious technical challenges. Outstanding experts in machine learning and discovery systems, Jarowski, Langley, and Todorovsky, argue that the output of discovery systems should be communicated easily to domain scientists. This is an important issue because traditional notations developed by machine learning researchers, such as decision trees, Bayesian networks, and so on, substantially differ from formalism typical to natural sciences, such as numeric equations, reaction pathways, and so on. In fact, this is a bit about out of the main subject because discovery systems are not exactly machine learning systems, although both kinds of systems are used in scientific research. Most work on computational scientific discovery attempts to generate knowledge in an established notation, but communicability is a significant enough issue for standard machine learning methods, independently of their admitted success. Okay. More on technical challenges. However, it's only at the end of 1910s, around 1915, a few years ago, that some researchers working in machine learning or data science or both, mostly in the United States, started expressing their worries that after decades of research, machine learning, undoubtedly successful, I would even say miraculously successful in various fields, in science are still at best capable of managing large data sets and detect very low level regularities in the data deluge, characteristic of the fourth paradigm, and in fact are perform not really better than old machine learning systems in the Turing tradition created in the 1970s using symbolic programming, especially logic programming and Prolog. Okay. For example, Karpatne et al. See that something is wrong. Some methodology used in scientific research by very advanced machine learning systems is wrong. Now what? Moreover, it turned out that in science, as opposed to commercial applications, commercial domains, standard black box methods may easily lose their predictive power in the face of new data, unlike business, unlike trading, and so on. The question is why? But before pursuing the question, just an example taken from that work of Karpatner et al. It's 8 authors. A famous example of failure in using data science methods in a theory agnostic manner is a famous program Google Flu Trends, where data-driven methods was learned to estimate the number of influenza-related physician visits based on the number of influenza-related Google search queries. The model was doing fine and finally stopped. There was serious discrepancy between predictive or estimated number of cases and real number, according to CDC, Center for Disease Control data. And this was symptomatic. Without deeper understanding of mechanisms of infectious disease, machine learning systems based solely on data and totally theory agnostic simply failed. Okay, the question is why? Excuse me, how much time do I have?
Since the presentation of Dr. Smith is not there, we shouldn't worry, and we started a little bit late. So
okay,
by the original time, you would be out of time, but by the current time, you still have like 10 minutes easily.
10 minutes?
Yes, easily. Mm-hmm.
All right, that's more than enough. Thanks a lot. Now, the authors cited a moment ago distinguish at least 2 characteristics of knowledge discovery that prevent standard machine learning methods from reaching level of success comparable to what they achieve in other domains. One characteristic is related to the fact that problems in science are typically ill-defined and more importantly, under-constrained. And as such, they typically do not provide many training samples, reliable training samples, and involve many potential variables which change in a complicated way. So we have problems with training systems, with training sets, reliable training sets. The second is that science, as opposed to commercial application, that in science, primary goal is searching for interpretable models and theories to explain, sometimes causally explain known phenomena and predict new ones, while in the standard black box methods of data science, merely aim at generating actionable models that have predictive power. To overcome these difficulties, the authors make an attempt to develop a general framework, which we call a new paradigm even. They call it TGDS, Theory Guided Data Science. They consider it an emerging paradigm in data science applications in scientific discovery by introducing scientific consistency as an essential component, along with training accuracy and model simplicity, for learning generalizable and scientifically interpretable models. Okay, the picture is important, so I stole it from the work of Karpatner et al. Just for the purpose of this talk. It illustrates the bias-variance trade-off in machine learning systems. Okay, TGDS, the new paradigm they promote, attempts to achieve better generalizability than model based solely on data by learning models that are consistent with scientific principles termed as physically consistent models. The authors illustrate the role of consistency with scientific knowledge in ensuring better generalization performance with an example of learning a parametric model for a predictive learning problem using a limited supply of labeled samples, which is typical in scientific problems. We have very limited supply of learning of labeled samples. Okay, what do we have on the picture? Ideally, we would like to learn a model that shows best generalization performance over any unseen instance. Okay, now we have simple model, more complicated models, and still more complicated models. And the more complicated model, the closer it approaches the truth, as depicted by the star here. Okay, but certainly we have a problem here, which is common to all machine learning systems, that, and this is called the bias-variance trade-off. The more complicated the model with smaller bias, closer to truth, but it has large variance, which means it's very prone to small changes in the training samples. The most complicated models belonging to M3, closest to the truth, show low bias, are close to the truth quoted, but high variance. They are rapidly changing with changing the training set. This is a well-known thing in statistical fact about machine learning. On the other hand, the simplest models belonging to M1 are quite robust to changes in the training set. So they show low variance. However, they have high bias, as it's generally are farther away from the true relationship. So we have lots of models, possible models. We hope they are close to the truth, but we don't know which one to choose because many of them are perform equally well on a training set. If we change a training set slightly, we have a completely different model. Okay, and here where TGDS comes into action. In scientific applications, we have an important source of information that can be used to ensure the selection of generalizable models. And this is available scientific knowledge. This is something missing in commercial applications. By pruning candidate models that are inconsistent with known scientific principles, shown as shaded regions here, we eliminate most inadequate models. And this way, we can significantly reduce the variance of models without likely affecting their bias. The last sentence is most important. Okay, now to summarize their ideas. The authors summarize the idea in a simple way by the following revised objective of model performance. We have performance and accuracy, plus simplicity, plus consistency, which allows for elimination of lots of unpromising models in science. Of course, the authors illustrate their thesis with a thorough analysis of lots of methods, at least 5 broad classes of methods of incorporating scientific data or theories or principles in model construction. This is a long story. I will not even discuss it in great detail because we don't have so much time, and I don't want you to bore you to death. 1, 2, 3, 4, 5 classes, okay. And I conclude that their paper presents the first step in building foundations of theory-guided data science and will anticipate the deep integration of theory-based and data science models to become a quintessential tool for scientific discovery in future research. The importance of domain knowledge of a theoretical character, which must be incorporated in modern machine learning methods, is also noticed in already mentioned on the second slide, the British Royal Society and Alan Turing Institute report, 2 years old, entitled The AI Revolution in Scientific Research. Now my conclusion. Do we have the end of theory? Definitely not. Theory-based and data-based models will have to complement each other in various ways. Now, last conclusion. Machine learning systems and discovery systems, which I didn't discuss here at all, are getting closer to each other. But this is another story. Thank you very much.
Thank you very much, Professor. Thank you. This was.
By the way, I'm not from Warsaw. I'm from.
You are
Lublin.
from Lublin, yes. I was trying to.
Studied theoretical physics in Warsaw, but I'm from Lublin.
Okay, thank you. Also, I want to welcome the new coming people in the audience, including Professor Mark Bergin, one of the leaders of the IS4SI movement for many years. So we will be interested also in hearing your opinion, Professor Bergin, on this and other topics in discussion. I think this is a very important goal that you've set up now, Professor Giza, and this is the theory-based data science, since many people, including creators of NARS in computer science, which is actually very successful, try to make a virtue of non-theory-based data science if the amount of data and comprehensiveness is good enough. So let me unfairly use my privilege to ask the first question. I really hope Professor Bergin and many participants would also follow. My first question would be, don't you think that theory dependency is somewhat of a problem, paradigmatic dependency, etc., and in particular, that the problem that you've seen in this, one of the last graphs that you were showing, which was very important, comes from the fact of big but not big enough amounts of data, that this is based not on really big data analysis, but just actually limited data analysis. So then the theory can be explained and its value as cashing out the other data that were not in it, even if they happened to be created 100 years ago or more. But if we have full data analysis, like what big data is trying to get, then that gap would not exist or will actually look differently. I know this is controversial. I don't have any stake in the game. This is just a natural question to pose at this point. Thank you.
Okay. If I understood your question correctly, yes, I agree with you. I agree with you. The problem of data in science and the data in commercial branches, like stock market, for example, is that in science, data without any interpretation, some people say is noise, at least some philosophers of science do, okay? So to see that something is data or noise, to see that something is important or not important, or an artifact, you already need some interpretation, okay? This is a well-known fact from philosophy of science. On the other hand, in commercial applications like stock markets, for example, or anything else, data is just data. Someone is ill, level of disease percentage is like that, okay? that number of people bought a certain product, and another percentage of people bought something else. Okay, so this is hard data already. So this is a problem. What is data and what is not data in science? This is already problematic. So to classify something as data, you already need to presuppose some perhaps very low-level theories. I wouldn't call them theories, perhaps experimental principles. Okay. So that's what I think. Now, enough data. The data deluge is that we have lots of data, too much data. Yeah, this is a problem. But any number of data, any amount of data may not be enough to construct a successful predictive model by just using black box techniques, as we can successfully do on any internet scale data in other fields. Yes, that's what I think.
Thank you very much. If I may just interject briefly, my advisor at Princeton, Bas van Frassen, was always arguing against this model, especially, you know, in this century, always in the 1990s actually, that we are trying to just find mathematical equations, and interpretation is always subjective. It's just a story, what Wolniewicz in Poland called glossolalia, and really the patterns matter. In our Congress, this will be represented in computer science by Ben Goertzel, who has his famous patternist philosophy as well. In computer science, this problem that you've mentioned is cast out as the problem of symbol grounding. But of course, I understand that in philosophy of science, this is deeper. I also studied with Amsterdamski at some point, so I know what that is. But the point is, while this was a very good theory, even 20, 30 years ago, isn't it exactly that saying of too much science sounds controversial, at least, because too much data, because actually every piece of data is just filling in the gaps, in kind of extra or interpolation, and so putting anything out is controversial, provided we of course discount data kind of like they do in the system NARS by not probability, but the level of trust in those data, and that level of trust may come from theory, but then the theory is in the background. Sorry, I don't mean to monopolize the discussion. That's a little bit of a question, a little bit of a statement, probably more of a question, and then we go to the rest of the audience. So is this a question that you would want to address at this point?
Sorry?
Is this the question that you would want to address a little bit? The paternist aspect, and especially the controversy about too much data. If the data is bad, we don't introduce it, of course. But if it is good enough as data, then putting anything out would not be fair, actually.
Yes, I agree with you. I didn't address this problem here. I didn't even think about it seriously, but it is a problem. I agree.
Thank you. I take it as a compliment. Professor Burgin, may we ask you for your contribution, if this is fair to ask? I know you came in the middle, but the topic is very important.
Yes, I have some question.
Yes.
And I have also a remark. The question is, don't you think that interpretation of data has always to be based on some theory? Maybe empirical theory, maybe an abstract logical mathematical theory, but interpretation has to be based on some theory. Is it true, or do you think it's something different?
Yes, Professor Bergin, I agree. This is something that has been discussed in philosophy of science for decades, okay? data has some component of theory, all right? But I believe myself that there are different levels of theory. Yes, we have high-level explanatory theories, adopting, for example, the ideology of Nancy Cartwright in her book, How the Laws of Physics Lie. Okay, we have high-level theories whose purpose is to explain. Then we have much lower level experimental rules whose purpose is just to describe phenomena, narrow classes of phenomena, because explanation is just broad and we have a gap between explanation and description, all right? So yes, I believe it. It's difficult to say data if we do not know what it is, okay? This is something what I said a moment ago when I tried to answer the question of Professor. Sorry, I don't know. There are more Poles than non-Poles here. I wanted to say Professor Boltuch.
This is correct.
I don't know. By the way, how to pronounce your name correctly in English? How do native speakers?
There is no corrective. I say Boltak for my students because otherwise they think I cannot speak English.
Okay, well, both Poles, allow me, please. As I wanted to answer Professor Boltak's question. Yes, I agreed that this is the problem of data. There is no data without interpretation, at least in science. The problem is what is important, what is not. For example, if you have billions events, particle collisions in Large Hadron Collider, what is important? Okay, what is significant, what is not? You need to presuppose some, I quoted in double quotes, theory, okay? At least some experimental principles that make sense of what is observed. It's unlike stock market, for example. Yes, it's unlike disease. That's what I said. It's unlike everyday life. Okay, better question.
Well, stock market and disease also require their thing.
Yeah.
I am a part-time professor of economic theory at SGH in Warsaw, so I actually have something to say about that. Probably interpretation is needed, but I would like to hear Professor Burgin's second part, maybe the comment. Would that be fair?
Yeah.
Yes.
And, first, I would like to say that I completely agree that there are theories on different levels of abstraction, and some are closer to data, some are far away. So this is how science is constructed. And my remark was that you mentioned inconsistent physical theories. And I want to tell that there are different techniques to work with inconsistent knowledge. And one of the technique is based on such logical construction that is called logical variety. And in it, logical varieties allow consistent structuring of inconsistent knowledge. So this is simply some addition to your interesting talk.
That's interesting.